Hello, and welcome to this presentation, Understanding Phase Noise, the Spectrum Analyzer Method. In this short presentation, we'll provide a technical overview of the spectrum analyzer, or direct spectrum method, and how this method is used to measure phase noise. This presentation assumes a basic technical understanding of spectrum analyzers and resolution bandwidth, as well as a basic understanding of phase noise. If you're unfamiliar with these topics, you may want to watch the presentation Understanding Basic Spectrum Analyzer Operation and/or the presentation Understanding Phase Noise Fundamentals before continuing with this presentation. The spectrum analyzer method is the oldest, most straightforward, and most widely used way to measure phase noise. The basic steps in this method are as follows. We start by measuring the carrier power of the device under test. We then move to a given frequency offset from the carrier, that is, to a point in the sideband, and measure the phase noise power contained in a 1 Hz bandwidth. If we subtract the carrier power from the noise power, the result is phase noise in dBc per Hertz at the given offset. Usually these measurements are repeated for various offset values, and the results can be displayed either graphically or as individual spot noise values in a table. When making phase noise measurements with a spectrum analyzer, there are, however, two additional steps that we need to take: normalization and shape correction. Recall that phase noise is specified as the noise power contained within a bandwidth of 1 Hz. Spectrum analyzers measure power using a resolution bandwidth filter, and this filter is usually more than 1 Hz wide. Therefore, noise power has to be normalized to a 1 Hz bandwidth. This is done by reducing the measured noise power value by ndB, where n equals 10 log of the resolution bandwidth in Hertz. For example, using a 3 kHz resolution bandwidth filter, we measure a noise power of -90 dBm. Applying our normalization formula, we get n equals 34.77 dB, so the normalized 1 Hz noise power is -124.77 dBm. In the previous slide, we showed resolution bandwidth as a rectangle, and this made the math very straightforward. However, real-world resolution bandwidth filters are not perfectly rectangular, often having a Gaussian or similar shape. So in addition to normalizing for the bandwidth, we also have to correct for the shape of the filter. For a given resolution bandwidth, a Gaussian filter has a wider noise bandwidth than its nominal or 3 dB bandwidth. This means we have to multiply our filter bandwidth by a scaling factor before normalization. The correction factor is implementation dependent. That is, it depends on how this specific filter was physically implemented. Not all Gaussian resolution bandwidth filters have the exact same shape. For example, the shape correction for this particular 3 kHz filter is 1.165. So in calculating n, we first multiply our nominal filter width by 1.165 before taking the logarithm. Note that most spectrum analyzers can automatically apply both types of correction, bandwidth and shape, by using a special noise marker function. We could therefore use this noise marker to manually make phase noise measurements. We would simply place the marker at the offset of interest and read off the normalized and shape-corrected value. However, like most other manual processes, measuring phase noise this way is both time-consuming and error-prone. Many spectrum analyzers, therefore, have a phase noise personality or option that automates the process, with the results presented in both graphic and numeric formats. Spectrum analyzers are general-purpose instruments, so the biggest advantage of using a SpecAn for measuring phase noise is that it provides additional useful functions for characterizing sources, such as measurements of spurious emissions, settling time measurements, and many others. In many cases, a traditional spectrum analyzer is sufficient for making phase noise measurements, but it's important to be aware of some of the challenges or limitations when using the spectrum analyzer method. These are dynamic range, instrument phase noise, close-in noise or drifting sources, and AM or amplitude noise. Let's spend a few moments looking at each of these. In the spectrum analyzer method, we calculate phase noise by measuring both the power of the carrier as well as the noise powers at different offsets from the carrier. The difference between the measured carrier power and the measured noise power is usually quite large, typically 80 to over 140 dB. And to make accurate phase noise measurements, we need to be able to measure both very high and very low powers simultaneously. Therefore, dynamic range, that is, the difference between the largest and smallest signals that can be accurately measured, becomes very important when choosing a spectrum analyzer for making phase noise measurements. Another important spectrum analyzer specification is the phase noise of the analyzer itself. Spectrum analyzers usually contain multiple local oscillators, or LOs. Like all other oscillators, each of these local oscillators has a certain amount of phase noise, and this phase noise is added to the phase noise of the DUT signal as it moves through the analyzer. One of the limitations of the spectrum analyzer method is that it's difficult to separate or distinguish the phase noise present in the original signal from the phase noise added by the instrument. The easiest and most common way of avoiding this issue is to ensure that the analyzer has better phase noise specifications than the device under test. At least 10 dB better is a good place to start, but the larger the margin, the more accurate the phase noise results. Measuring phase noise at very small offsets from the carrier, or close-in phase noise, can be very difficult for two reasons. First, a very narrow resolution bandwidth filter needs to be chosen to avoid measuring the carrier power as well as the noise power. The fact that resolution bandwidth filters have a Gaussian rather than a perfectly rectangular shape also complicates this issue. An additional challenge is measuring the phase noise of a carrier that drifts slightly in frequency, although some analyzers do have the ability to track a small amount of drift and automatically compensate for it. Modern spectrum analyzers can avoid some of these issues by measuring phase noise using so-called IQ data. IQ data is a digital representation of the spectrum and is obtained by means of the fast Fourier transform. Measuring with IQ data can improve the stability and the accuracy of phase noise measurements, particularly for close-in measurements or for drifting sources. This same IQ mode is also useful when it comes to AM or amplitude noise. When measuring phase noise, we assume that the noise sidebands around the carrier are mostly due to phase noise, but with some amount of amplitude noise mixed in. And in general, this is a valid assumption. The AM noise in real-world devices is usually much less than the phase noise. In some cases, however, this may not be true, and if a large amount of amplitude noise is present, the standard spectrum analyzer method may not produce accurate results, because this method cannot distinguish between AM and phase noise. Separate measurements of AM and phase noise usually require the use of a different instrument, that is, a dedicated phase noise analyzer. But a traditional spectrum analyzer can reject some AM noise if the measurement is made with IQ data. It's worth noting that the influence of AM noise is usually greatest at higher frequency offsets from the carrier, so the benefits of this approach become more noticeable the further out we measure. Let's end with a brief summary. Traditional general-purpose spectrum analyzers can be used for making phase noise measurements. This is done by measuring the power in a 1 Hz bandwidth relative to the power of the carrier at a given offset. Since spectrum analyzers don't possess a perfectly rectangular 1 Hz resolution bandwidth filter, bandwidth normalization and shape correction are required. These are normally automatically handled by the instrument, either in the form of a noise marker or as part of an automated phase noise measurement routine. For many types of DUTs, spectrum analyzers can provide good phase noise measurement results, although the instrument should have a high dynamic range and low internal or intrinsic phase noise. In addition, the ability to measure phase noise using IQ data can be helpful in certain scenarios. For more demanding phase noise measurement applications, dedicated phase noise analyzers and the cross-correlation method can be used to provide additional speed, accuracy, and sensitivity. This concludes our presentation, Understanding Phase Noise, the Spectrum Analyzer Method. Thanks for watching.